At the end of the previous video, we determined that of the variables available, we're going to choose these x1, x2, x3, 4, 7 and 8 as the variables with which we're going to develop a model. The other variables we removed them due to multicollinearity problems. So here we did the VIF and we got rid of one variable at a time to arrive at a set that has reasonably small, even though there are a couple of them which are kind of high, still because of their association, strong association with the dependent variable, the price of unleaded gasoline, we're going to retain those. So here is the list of variables and we have renamed them as Z1 through Z6 so that we will be able to relate back to what they were originally. So this is a kind of convenience step, not necessary but definitely useful in terms of making sure that we don't get mixed up with the variable names. Okay, so what's the next step? Now that we have narrowed down the variables, and how do we develop the best model from these 6 dependent variables? Okay, and that's what we call variable selection. So let's go to the Word document for a minute. Okay, selection of variables. So we are going back to section 9.4. With section 9.5, we looked at multicollinearity, and that's your step 1. So step 1 in the selection of variables process, because it's a 2-step process. First step is to study the correlations, prepare the VIF, and then drop one variable at a time, okay, variables that have very high VIF. And the thumb rule that we used was greater than or equal to 10, even though that's only a thumb rule, there is nothing sacred about that. So we actually allowed a couple of variables with 20 and 30 as VIF, and in step 2, if some of those variables get thrown out, that's fine. Okay, so we are at the end of step 1. We have repeated the VIF and we have a set of 6 variables. So now we do step 2, which is model selection methodologies. So we have 3 different approaches that we can follow: forward selection, backward elimination, and stepwise regression. So in forward selection, the idea is you start with all the 6 variables there, so you select the best of those 6 that gives us the largest R squared value, okay, and select that one variable into the regression analysis. Okay, so now you have the dependent variable and then one independent variable in the equation. So you have a model with only one independent variable. So once this variable is already in, now you look at the balanced variables, the variables that are not yet included. Okay, so if you started with 6, you've taken 1 in, and we'll have 5 remaining. Now with this one already in, what is the next best variable that we can include? So include that. Okay. The best here meaning the one that will improve the R squared value by the largest amount. Okay. And you keep repeating this, okay, until, so you will have a threshold value, okay, that indicates a significance level. So if the variable that you are bringing in, as long as that variable's p-value is less than alpha, you'll keep bringing the variables into the equation and build the model going from 1 independent variable to 2 independent variables, 3, 4, and 5, and so on. And you do so only until the p-value, as long as the p-value is less than alpha. So once you hit a stage where the best variable that you want to bring in has a p-value that's greater than alpha, then you stop. Okay, so this is forward selection. So you won't include all the variables into the equation unless even the last variable has a p-value that is less than alpha. So this is forward selection. Now backward elimination is you do this backwards. That is, you start with all the variables in. Okay, then examine which variable, if taken out, will have the least effect on R squared. The R squared will go down by very little. Okay, so that's the best variable that can be thrown out. In other words, the worst variable to keep inside. Okay, so you throw that out. Okay, and then repeat the process. And once again, you have an alpha value threshold set. So you keep throwing the variables out as long as the p-value of those variables is greater than the threshold alpha. Once you hit a stage where the variable that you want to throw out is a significant variable because the p-value is less than alpha, then at that point you stop. So this is backward elimination. A third approach is stepwise regression, where we combine the forward selection and backward elimination in every step. So you start with, like in the forward selection, the best variable comes in first. Okay, and then the second best then is put in. So once you put the second best in, then you do a backward elimination step. You see whether the other variable can be taken out, meaning the p-value, if that variable is taken out, p-value is going to be greater than alpha. Okay, so you try to take the any one of those variables out. Okay, if that fails, then you do the forward selection as the next step. So you bring in the next one. So every time you bring in a new variable in, you need to try and see whether any of the variables that are already in can be taken out. Meaning that the p-value, if taken out, the p-value of that variable that you're taking out is greater than alpha. So you have forward step and then the backward step. Forward step and a backward step. And you do that until you reach a point where there are no variables that can be brought in that has a p-value less than alpha. So even the best variable that stays out has a p-value greater than alpha. So you can't bring that variable in or any of the variables in. And conversely, looking at all the variables that are already in, okay, there is no variable that can be taken out such that the p-value of that variable is less than, is greater than alpha. Okay, the variable that you, the best variable, or the variable that has the least impact on R squared, even that variable has a p-value less than alpha, deserving to be kept in. So there is no variable that you're able to bring in with a p-value less than alpha, and you have no variable that's already in that has a p-value greater than alpha such that it can be thrown out. At that point, you stop. So these three approaches can be used, and the best model that each of them gives, oftentimes they all may come up with the same model, in which case great. But sometimes different approaches will give you at the end different combination of variables in the model, in which case you have to do some more analysis to see which one would be the best among the three models. There is one more extension that you can perform to the forward selection, and that is called searching for all possible models, the best subset regression. So this differs from forward selection in the sense that what we're trying to do is we want the best one variable model, okay, which is easy enough. That's your first step in forward selection. So you keep that aside, and then now go back to all the variables. Now you look at all the possible two variable models, and among those two variable models you select the one that has the largest R square. So when we start with k independent variables, there are k possible models with just one independent variable. Okay, and then for two independent variables, so you have k variables taking two at a time, that is k combination 2, and that will give us k times k minus 1 over 2 possible models with two independent variables. Okay. Now that's the best two independent variable model. Now go back to all the k variables. Now this time you take three variable at a time, all possible three variable combinations. Okay, and then among those three variable combinations, select the one that is best, that is the one that has the largest R squared value. So if you keep doing this until you get to all k possible independent variables in the model, so at the end you would have had to run the regression 2 to the power of k minus 1 times. That's the number of possible regression models available of all sizes included. And that's a very large number, so often it is very difficult to complete this analysis, and therefore what we could do is as a kind of as close to all best possible models as possible is to do a forward selection, except make sure that you set the alpha threshold really high, so you will have a model of each size. You will have a model with 1 variable, you will have a model with 2 variables, you will have a model with 3 variables, and so on until the k variable. The only difference is when you get to the 2 variable model, in best subset regression, you would have had to consider all possible 2 variable models. But in this watered down approach, we will only be looking at 2 variable models with the first variable already in. Then you look at all the other variables and then see which one is best. And when you get to 3 variable model, instead of looking at all the 3 variable models, you only look at 3 variable models where the first 2 variables that you've already selected are already in, and you look at only the remaining. So this is not strictly the best subset, but since the best subset approach is going to require us to do large number of computations, this is kind of a diluted or watered down best subset approach. Often this is not going to be very bad, so it will be pretty good, this approach, even though it's not strictly best subset regression, it still gives you very good results.